Hi everyone. Today we're going to look at Unit 4, Target 3, which is applying the conservation of energy to analyze a system or compare between systems. Specifically, in this video, we're going to focus on applying the conservation of energy. I think it's best to look at conservation of energy in the context of a problem. So here we're going to look at a case where a box is going to go down a hill, over a rough patch, down another hill, up a hill, and back down again. And what we want to know is if this box is 10 kilograms and the spring is initially compressed 3 meters, how fast will that box be traveling once it reaches point D right here? So that's our goal for this problem, and we're going to use conservation of energy to solve it. What we'll do is we'll start by applying our LOL diagram, and that'll help us think about where energy is in the system and what energy is out of the system and what energy is being added to the system and what energy is being removed from the system. And as usual, I recommend that you put all the objects in the system that possess or encompass mechanical energy. So in this case, that would be the box, the earth, and the spring. Initially, we see that the box has some height, or delta y, above point D, so it's going to possess or have some gravitational potential energy to start with. Similarly, the spring is compressed, and so as a result, the system will have some U spring stored in it. As the box slides across this rough patch down here, friction is going to do work on the box, which will remove some energy from the system. So we've diagrammed that there in the O of our LOL diagram. But in the end, there will still be kinetic energy. Once the box reaches point D, it will be moving. So we can then use our LOL diagram to guide us in working through our conservation of energy equation. Energy initial plus work equals energy final. And we see that in our first L, the initial energies are UG plus U spring. We then see that friction is doing work to remove energy from the system, and we're left in the end with kinetic energy. Notice, as I always mention, that we make the work positive, or we put a plus in there, because we're anticipating that if this is doing negative work, if friction's doing negative work, or if it's removing energy from the system, that our calculations will show that it's a negative value. Okay, so let's go ahead and elaborate on our equation. We know UG is mgh, or mg delta y. We know U spring is 1 fkx squared, and we know that work is the force parallel times the displacement, and kinetic energy is 1 fmv squared. So we have a lot of those values, and we can plug a lot of those values in, like mg delta y. We know the mass of the box, we know the gravitational field strength, we know that the height is 27, right? That's given to us right here, the height that it's going to go down or change its y position. We know the spring constant is 2,000 newtons per meter, and we know that it's compressed 3 meters. And we know the mass of the box is 30 kilograms. So we can plug all those values in. What we need to do is we need to do a little more thinking about the mu times force normal parallel to the displacement. So let's do a little more thinking about that. First of all, the way we're going to solve for the normal force is by recognizing that since the box is on a flat surface, the normal force is going to be equal to the force of gravity. Again, it's not on an incline, it's on a flat surface, so those two things are going to be equal to each other. So if we can find our force of gravity, which we can by doing mass times the gravitational field strength, then we can also find our normal force, which we can now go ahead and plug in those values. We see mu is 0.5, we see that the normal force is 294, and it travels across a displacement of 32 meters while it feels the force of friction. However, there's one more thing that we need to be very aware of, and it's this parallel sign. How is the force of friction, how much is the force of friction parallel to the displacement? Well, friction is going to point backwards, and we know it's displacing forwards, so force of friction and displacement are completely parallel to each other. But they point opposite directions. So they're really kind of like anti-parallel to each other, which means that we need to make sure that we insert a negative sign in front of that. And that negative sign makes perfect sense because, as we noted earlier, the work of forced friction is taking energy away from the system because it's slowing it down. And that's still equal to 1 FmV squared. And now we've got all our values, and the only unknown is velocity. So we can just do some algebra and solve for that velocity. And we find that the velocity of the block at point D is 28.6 meters per second. There you go. This hopefully helped you with Unit 4, Target 3, and I will see you later. Bye.